Real quantum mechanics, revisited from the perspective of the detector, and published. Richard Feynman said quantum mechanics is crazy. It doesn't explain anything. It just gives you numbers. Einstein was more critical. The wave function does not provide a complete description of the physical reality. We'll return to these. Meanwhile, we'll start by comparing Matthew maxim with physical principle. And then we'll proceed to discuss the wave packet with internal motion, which is quantized by harmonic states, sometimes dual harmonic states, and detected in time continuously. We'll wrap up with the logic of quantum physics. The mathematical version of quantum mechanics in red is given by 4 axioms by Carroll, and the third axiom is uncontentious. Unitary evolution of isolated systems is deterministic and continuous. This is typical of all physics. What about completeness? It's ambiguous. If what they mean is that abelian matrices solve in closed groups, well, there may be something in it. But that's not what Feynman thought. He thought he couldn't predict the future changes in quantum theory. And Einstein will deal with in a moment. But if the axiomatic theory is complete, then by Gödel's theorem, it cannot be consistent, and that's not acceptable. Well, what about measurement? If the emission operator A, with spectral projectors pk, is measured, the probability of outcome k is this bracket. These probabilities are objective and indeterminate. Well, that's the theory. But in Einstein's thought experiment, this objectivity required avoiding conservation laws and randomizing reference frames. Well, that seems to us not objective but subjective. Let's go on to axiom 4. Evolution of systems undergoing measurement are discontinuous and instantaneous. How can that be, given the uncertainty in time due to Heisenberg's limits? We show that the evolution is continuous in time within an uncertainty which we shall derive and influenced by hidden variables. Well, let's go on to wave-particle duality. We begin by uniting Newton's corpuscles, Huygens wavelets, Fraunhofer's and Fresnel's diffraction, Young's slit, Lloyd's mirror, Maxwell's electromagnetism. By the end of the 19th century, it seemed to be fairly complete, this theory. However, when the quantum was discovered, problems arose. Planck's law, the de Broglie hypothesis, Einstein's special relativity, energy squared is momentum squared plus mass squared. This formula, with simplified units, gives the equation for mass. Mass squared is equal to angular frequency squared minus wave vector squared. And this is separable into 2 parts, a conservative part and a response part. The conservative part describes mass, charge, spin, energy, momentum. The response part describes interference, superposition, creation, annihilation, entanglement, and resonance. The conservative part is a envelope function, it's a wave group. And the response part is an infinite complex wave which has amplitude unity for all x and t. The uncertainty is 2 sigma. And we can operate on this equation in many ways, but for this paper we're interested in the Fourier transform and differentiation. Start by noticing that omega bar and k bar that we used in the formula are mean values of varying functions. From the figure, as we saw, the expected uncertainty d-tau is 2 sigma. The Fourier transform of a Gaussian is Gaussian, and we can transform this function with this Gaussian transformation, and we find that the uncertainty in angular frequency is 4 over sigma. Multiplying these two, we get that the omega dt is equal to 8. This is the expected uncertainty. It's an order of magnitude greater than Heisenberg's limit. I'll say a little more about that in a moment. The second transformation we make is differentiation. If we differentiate this formula, we get a very important result. The product of the phase velocity times the group velocity is equal to c squared, which we put equal to 1. Well, what is the group velocity? That's the velocity we use in relativity. It varies between 0 and c. And the phase velocity is frequency times the wavelength, omega over k. The phase velocity is greater than c. It varies between c and tends to infinity as the wavelength gets very long. So that's true for photons and electrons. In photons, the mass is 0, so the phase velocity is equal to the group velocity, is equal to c. But in electrons, the phase velocity is greater than c, is greater than group velocity. And this shows that there are limits as lambda increases. Well, what are examples of the quantum? Schrödinger's spherically harmonic eigenstates of hydrogen, line spectra and atomic emission and absorption, the wave packet we've just seen. And we'll go on to momentum quanta and crystal diffraction and dual ionics, harmonics and hierarchic quasi-crystals. The diffraction pattern is a map of momentum quanta transferred during the diffraction. They follow Planck's law. N is an integer. 0, 1, 2, 3, 4, 5, 6. In this instance, odd orders are suppressed by structure factors because half the atoms are in antiphase when they scatter. In a crystal, the probe is harmonic, the crystal is harmonic, the diffraction pattern is harmonic, and the harmonies are extremely well understood in crystallography. Quasi-crystals are completely different. N equals 0, 1, tau, tau squared, tau cubed. Tau is irrational. The structure is hierarchic, it's aperiodic, and it follows not Bragg's law but a quasi-Bragg law, which is irrational. Well, how do we understand that irrational diffraction pattern? The first thing you can easily prove by mathematical induction is that this irrational number is equal to this Fibonacci sequence. Here it is 1 tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, 3 plus 5 tau. And this contains a partly rational, natural part and partly irrational. But if we substitute for tau the rational fraction 3/2, we can approximate a natural part. And if we subtract from the irrational part, we get the irrational residue. This has a very important consequence and a very extraordinary consequence. The irrational residue is used in the metric function, which is exactly the same, or the exact inverse of the coherence factor that we discovered numerically from the hierarchic structure. The metric function provides a 12% divergence from the Bragg angle and verifies both the structure and the diffraction. I can illustrate. Look at the blue wave. This is a block wave due to a crystal at a two-beam Bragg condition. It's commensurate with a unit cell and with all unit cells periodically repeating, but incommensurate with the intercepts of the quasi-lattice. However, if we multiply the blue or stretch the blue block wave by the metric function that we just derived, we find a quasi-block wave which is commensurate with all geometric lattice intercepts, both long range and short range. And the result of this theory and verification is that perfectly understood harmonies in Bragg diffraction confirm all quanta are harmonic, and momentum quanta are the most easily understood. So now we can understand a little better the Young slit experiment. Fire a coherent beam onto two slits. They separate into two Huygens wavelets and produce an interference pattern. If you square this trigonometric function, you get the interference pattern. This is the pattern that will occur on your retta if you were to look at the slits, but I don't advise you to do that. However, if you can reduce the intensity of the incident beam, the image occurs as dots on a scintillation screen, time resolved. And when you count for a long time, this pattern resembles the laser pattern. In quantum mechanics, these slits produce two results. Let us suppose that because the detected signal is localized, that the quantum is localized. It's a point particle. Then when the point particle goes through B, how does it know whether to produce this interference pattern or that interference image? It would have to know whether A was open and closed. If A is open, you get this pattern. If A is closed, you get that pattern. How does it know? Well, that's one problem. And the second problem, once these interference occurs in these beams, how are they reduced to a single slit in the case of weak beam detection? The mathematicians say, oh, well, you can't measure it, it doesn't exist. That's spooky. The whole thing is spooky. So let's see what the physical explanation can be. Remember that the photon is time resolved. So it's the quantum, the wave group is spread over time, and the photon or electron has time to interfere with the image screen and resonate with it. And when it resonates, it swaps energy from the photon group to the scintillating molecule, and there's a backwards and forwards resonance which transfers the energy from the photon to the resonant molecule, which then fluoresces. So let the point particle be a point at the center of the wave and not a point particle to rid these anomalies instantaneous, indeterminate, and spooky collapse. In fact, in physics, we have an evolutionary wave packet which resonates long range with the detected scintillator screen. So with that, we can go on to describe a logic of measurement. Wave-particle duality is co-expressed by probability amplitudes. Quanta of energy or momentum are a consequence of harmonic geometries. The discovery of quanta implied two anomalies: spooky action at a distance and unpredicted behavior. A hidden variable can be expressed by a probability wave function. In physics, every event has a rational explanation. In mathematics, any event can be given multiple explanations. And in the logic of empirical physics, two or more explanations that make the same prediction are equally true, logically true. Localization of quanta is a product of hidden variables in time, at emission, propagation or detection, for example, etc. Mathematical state evolutions that are nominally discontinuous and instantaneous on math are timely in physics. And we have a final conclusion. We have a physical model for reduction, and we have a definition of mass.